Hello, welcome everybody. My name's Margaret Shield and I'm the Provost here at the University of Melbourne, and it's my very great pleasure to both welcome you and introduce our speaker for this evening. I begin by acknowledging the traditional owners of the land on which this lecture is taking place, the Wurundjeri people, and I pay my respects to the Wurundjeri elders past and present. Jim, if you learn anything about Indigenous culture while you're here, they were also, it's a very old scientific culture in terms of their knowledge of the land, the stars and medicinal plants and many other aspects of the kind of culture that you need to have to survive in the kind of landscape we have here. So I urge you to learn a bit more about that when you're here. One of the wonderful things about the University of Melbourne is I'm always constantly surprised by what we're doing here and what is on offer and the range of lectures and various other activities that we undertake. And so I was delighted earlier this year when I was asked to host this lecture. I had just actually returned from a trip to Europe with my daughter, and we travelled to Morocco on a rather rough tour for me. I had to climb up mountains, camp in deserts and do a few other adventurous things. But one of the more interesting aspects of that trip was that we stopped in a very remote village outside of Marrakesh in the southern part of Morocco, and the tour guide said, "Oh, you should come in here. We're stopping. It's not on the trip, but there's some very interesting things to see here, including a hospital, but also a library." And so it's literally in the middle of the desert, small village, which was sustained by tourism and some pottery. And we met this Moroccan guide, and he took us into the library, and it was full of all these texts that dated from 11th, 12th century, full of astronomy and physics and various other, I could recognise the diagrams, I couldn't read the text, and I kept asking the guide what was in this, and he'd say, "Oh, that bit's mathematics, and that was astronomy, and that was," I don't think he said physics, but I couldn't detect too much chemistry in amongst the words. And so I was just intrigued by this and the age of the text and the age of the science that must have gone on and been described there. So when I went back to London and I was in a bookshop, I picked up this book, which was Jim's book, and I knew little about him then, but I picked up the book, The Golden Age of Arabic Science, and read it on the plane on the way home. So when I got home, then I had an email asking me to introduce tonight's lecture. So it was a lovely piece of synergy, and so it's a great delight to have you here after having read your book and pondered something about Arabic science while I was in Morocco. So Jim was born in Baghdad. He took his bachelor and doctoral degrees at the University of Surrey, and we just had a conversation about what a wonderful institution that is and their commitment and support for his work. In the 1990s, Jim held an advanced research fellowship from Britain's Engineering and Physical Sciences Research Council, and he's an active researcher in nuclear physics. And I would also acknowledge my science colleagues here, Professor Karen Day, who will thank Jim at the end of our lecture, and David Jamieson from the School of Physics. Jim won the Michael Faraday Prize from the Royal Society in 2007 for excellence in communicating science, and he's in excellent company in winning that prize, with others have included David Attenborough and Richard Dawkins. We've also had several other leading British science communicators at Melbourne, including Martin Rees and Brian Cox, both of whom have also won the Faraday Prize. Jim holds a chair in public engagement and science at the University of Surrey. He's a president of the British Humanist Association. He hosts a regular interview series on the University of Surrey's YouTube segment channel, where I did a little Googling this evening and saw that you've interviewed, amongst others, the Archbishop of Canterbury and a range of other prominent scientific and public guests. He has hosted and contributed to many documentary and television programs, including Chemistry: A Volatile History, Shock and Awe: The Story of Electricity, and a 4-part documentary on the science of Doctor Who, which I wasn't quite sure there was any science in Doctor Who, but I must download that and have a look at that. He's also presented the 3-part BBC series Science and Islam. His books include Paradox: The 9 Great Enigmas of Science, a book called Black Holes, Wormholes and Time Machines, and I think we'll hear something of that tonight, and The House of Wisdom on Arabic Science, which was also published as Pathfinders, which is the version I have. As universities think and rethink our work in science and the importance of the public engagement in science, it's wonderful to have Jim here as an exemplar of that practice, and that practice, a rare and important series of talents. So I'm delighted to welcome him here to the university this evening, but before I do that, I have to say 2 things in terms of housekeeping. The first is to let you know that the lecture is being filmed and live streamed, and the second is that you can follow it with hashtag Al-Khalili. Correct? I'm looking at my Chris here for my instructions. So it's a great pleasure to welcome Jim to the University of Melbourne and his wife Julie to Melbourne, and please join me in looking forward to the lecture, Time Travel: Separating Science Fact from Science Fiction. Thank you, Jim.
Thank you very much, Margaret. Well, good evening, everyone. Yes, this is my first visit to Melbourne, our first trip to Australia, in fact, and my wife and I this morning took some time, went to Melbourne Museum, so we did learn a little bit about the cosmology of the Indigenous people here, and it was a very, very beautiful sort of sound and light show well, it was very pretty anyway. So this evening's lecture, Time Travel, Separating Science Fact from Science Fiction, is one that I've given for a number of years, and in fact, as Margaret mentioned, I have a book called Black Holes, Wormholes and Time Machines. It was my first book, 15 years ago now it was published, and it was based on a series of schools lectures that I gave. My area, as Margaret mentioned, in my research specialism is nuclear physics and quantum mechanics. So cosmology and Einstein's theories of relativity are not my research specialism, but it's a subject that I have lectured on for many, many years. I want to delve into, I think anyone who has any interest in science will probably follow science fiction movies and read science fiction novels and be aware of the various stories and ideas about the possibility of traveling through time. So I want to explore what modern physics has to say about this subject, how much of these ideas of time travel are just complete nonsense, and how much are actually based on our current understanding, our current best theories of the nature of space and time. I think it's fair to say that pondering the meaning of time is not something new. It's not something that is the reserve of modern physics. Scientists, theologians, philosophers, and all deep thinkers over millennia have tried to understand what it means. What is it? Does time flow? What is the rate at which time goes by? I think one wag famously said, time goes by at the rate of 1 second per second. It's a very, very stupid thing to say. It doesn't mean anything at all. It's also fair to say that I think most of us have this common sense, sort of logical picture of time being some cosmic clock that ticks by the seconds, the minutes, the hours, the years at the same rate for everyone. Julie and I are trying to get over our 9-hour jet lag, and we know that time zones around the world are basically mankind's invention to make sure that each part of the world has the same sort of hours of day and night. But we still think that there's this cosmic clock that measures time going by at the same rate for everyone. And for instance, if you enjoy this lecture and time goes by quickly, but if you're bored and wish you'd watch some football match on TV instead, and time is going by slowly, you know that that's only your own subjective view of how fast time goes by. You know, that's something internal to your brain. Time isn't really speeding up and slowing down. Well, That picture of the nature of time is the picture that we learn from Isaac Newton. The nature of time as an absolute, as separate from space that goes by at a constant rate. We know now that that picture of the nature of time is wrong, because 100 years ago, over 100 years ago, that picture was changed. Albert Einstein, who I guess is the most iconic, most famous scientist in history, we think of him as the old man with the thick tash and the wild hair. But in fact, the Einstein who changed the world of physics was quite a debonair, handsome-looking young man, at least as handsome as I could sketch him. In 1905, Einstein published a number of papers that changed science forever. He was working as a patents clerk in an office, a job that he found very boring. It was also a job that didn't really utilize all his time. He couldn't get a university job to begin with. He had a lot of spare time on his hands to think deep thoughts. He published a paper in which he proved mathematically that atoms exist. And it's quite surprising to many physicists and chemists today to think that actually by the turn of the 20th century, it wasn't clear that matter wasn't infinitely divisible, that you take a piece of stuff and divide it in half and half and half again and again, and that you derive out a fundamental building block, atoms. Einstein used mathematics to prove, he was explaining a concept called Brownian motion, to prove that in fact matter was composed of these elementary building blocks that had been proposed since the ancient Greeks. He also showed that light was also made of its kind of atoms. Light is made of particles, lumps of energy that can't be subdivided, lumps we now call photons. That work, that paper he published, would eventually end in him receiving the Nobel Prize some years later, explaining something called the photoelectric effect. And none of this stuff is really, I haven't got to the work that Einstein is really famous for. His revolutionizing the nature of space and time. Einstein's theories of relativity, and there were two theories of relativity, really overthrew the Newtonian picture of the universe. Einstein said that time and space are mixed up together. Space isn't the stage on which things happen, and time is that clock that ticks by independently of events unfolding within space. Time and space are mixed up. They cannot be separated. This led to an idea in which you can imagine the whole universe, not as 3 dimensions of space plus 1 of time, but as a 4-dimensional space-time. Of course, we can't imagine 4 dimensions of space-time. I know there are some people who claim they can think, imagine what, or visualize what four dimensions are like. Nonsense. They're lying. You can't. Our brains are 3-dimensional, and you can sort of get an idea for what the shadow of 4 dimensions, the projection of 4 dimensions are in our 3-dimensional world, in the same way that a shadow to us is a 2-dimensional projection of 3-dimensional objects. Anyway, we can try and visualize what 4 dimensions are like by throwing away one of those dimensions and imagining our universe, our space, being just flat 2 dimensions. So imagine that block is our universe. In fact, it's called the block universe. That back surface is the whole of space, which I've squashed down just to 2 dimensions, allowing me the 3rd dimension to be time. So this is a projection onto a 2-dimensional surface picture of a 3-dimensional block that's depicting 4-dimensional space-time. Once we get to once we get to bending 4 dimensions to a 5th dimension, then I'm happy to lose you. I'll try not to get into too many dimensions. I won't be talking about string theory, for instance, which is 10 dimensions, or 11 if you're really keen. So what does this mean? Well, it means that time is another axis. In the same way that space, I can talk about going left and right, up and down, forwards and backwards, our 3 dimensions of space. Time is another axis. So you can imagine a slice through this block that is the now. So it's all of space at a particular point along the time axis. And that now, our consciousness of when the present moment is, creeps along the time axis. What has come before is the past. What is yet to come is the future. Me, here and now, is some point at the now moment, at some point in space. This idea is very useful in physics, and Einstein was one of the people who took it quite literally. But it does suggest something quite profound. It suggests that it's not just our present moment that is real. We think of only the present moment is real. What's past is gone, is finished. Maybe living in our memories, but it no longer exists in a real sense. What is yet to come, what is in the future, has yet to unfold, and is also, therefore, not real. This picture suggests that, in fact, that's just our own perception. In fact, in reality, all times coexist. It leads to all sorts of strange ideas. For instance, does it mean that the future is already fixed, it's predetermined, and therefore that we don't even have free will because there's an inevitability about how the future will unfold, despite our thinking that we're actually making free choices? That's a whole nother lecture, and I won't go into the nature of free will. Einstein's theory of relativity, in particular for the purposes of this talk, tells us something profound about time itself. That time need not go at the same rate for everyone. It depends on what we call your frame of reference. It depends on how fast we're moving relative to each other. To give you an example, if I were to strap a clock onto a rocket and have it fly past me close to the speed of light, the speed of light being the maximum speed in our universe, and it's the speed at which all these strange ideas about Einstein's theory of relativity really kick in. So I need a rocket. If I want to see time running at a different rate, I need that rocket to fly by close to the speed of light. Imagine having a clock on that rocket as it goes by. If I compare that clock with an identical one that I have on the ground with me, I'll see the moving clock ticking by the seconds more slowly than the one I have next to me. So time slows down as something approaches the speed of light. This leads to answering one of the questions about time travel, because if you'd ask, well, is time travel possible or not? The answer is it depends on which kind of time travel you mean. Do you mean time travel into the future or time travel back into the past? The slowing down of time allows us a means of getting to the future. Imagine that rocket that's traveling close to the speed of light. Imagine someone in that rocket. They don't feel any different. To them, time is going by normally. But if you were to speak to them and they speak back to you, they will be speaking in slow motion. They'll be doing everything in slow motion, even though they don't think there's anything strange. This leads to a very famous example in relativity theory called the twins paradox, whereby you have twins, Alice and Bob. It's always Alice and Bob in physics. Physicists are snickering because they know. Alice, A and B. You see Alice and Bob, A and B. If you need a third person, it's always Carol, then often Donald, and so on. Anyway, Alice is the adventurous one of the twins, and she's in the rocket that flies, let's say it zips around the galaxy close to the speed of light for 1 year. So she, as far as she's concerned, she's been in the rocket for a year. The clock on board the rocket, the computer, her body clock, her biological clock, everything there has aged 1 year. 1 year has gone by before she returns to Earth. Her twin brother, Bob, has remained on Earth. Now, she is 1 year older. When she gets back to Earth, because of her moving around the galaxy close to the speed of light, her clock will have run more slowly than the clock on Earth. And so 1 year has gone by for her, but maybe 10 years have gone by for Bob on Earth. So she returns to Earth, and Bob is now 9 years older than her. He's aged 10 years, she's aged 1 year. And that 1 year and 10 years is arbitrary. It depends on how close to the speed of light she travels. If she could nudge ever closer to 99.9999% the speed of light, we don't have the technology for a rocket to go that fast, but in principle it's not breaking any laws of physics. Exceeding the speed of light is breaking laws of physics. which is why so many generations of physicists get upset with Star Trek and dilithium crystals and warp drive. Yeah, I know, it's scandalous. So Alice could have zipped around in her rocket for half an hour, come back to Earth, and 1,000 years, 1,000,000 years have gone by on Earth. Because by slowing her time down, she has essentially moved out of Earth's time stream into a different rate of the flowing of time and has fast-forwarded and got to the future before everyone else. As far as I'm concerned, that's a means of time travel. The question is, if she gets to the future, is she able to come back to the past? Well, that actually is a lot more tricky. Now, this was Einstein's special theory of relativity in 1905, the slowing down of time. A lot of ideas such as this, whether the future is predetermined and whether we had free will, bothered a lot of physicists. The other big theory in physics in the early 20th century is quantum mechanics. Now, quantum mechanics is the theory of cats being dead and alive at the same time. It's the theory of the title of the gentleman here's t-shirt, I'm uncertain about quantum mechanics. It's the theory that describes the subatomic world, the world of atoms and the particles that make up atoms. And it's a very, very strange theory, and also the subject of a different lecture. Quantum mechanics, if we ever thought relativity, Einstein's theory of relativity was strange, quantum mechanics really messes with your head. My favorite picture that describes quantum mechanics is this, the quantum skier. It's very interesting how the tree is intact and he doesn't seem to have suffered any ill effects. But in the quantum world, that sort of thing happens. Particles going two ways at once. Somehow the start is fine and the end is fine, but something weird goes on in the middle that we can't explain. Quantum mechanics also is about uncertainty and chance and probability. So quantum mechanics explains how an atom that is radioactive, that its nucleus wants to spit out, say, an alpha particle because it's unstable, doesn't do so at any pre-prescribed moment or any moment that we could predict in advance. If we have trillions of atoms, a lump of radioactive material, we can very accurately calculate what's called the half-life. So we can work out how long before half of the atoms in that lump of material will decay. Statistically, we can get an accurate number. But look at an individual atom, and you could never know in advance when that's going to happen. Not because our theory of quantum mechanics is found wanting, that it's somehow approximate, but because nature herself hasn't yet decided when that atom's going to spit out the particle. Many physicists said, well, this opens up the future. Einstein's predetermined, preordained, fixed future is wrong because quantum mechanics allows us the freedom for different things to happen that we can't predict. In fact, these quantum effects, this indeterminacy of the quantum world, seem to be trapped and constrained within the subatomic world. So apart from certain special examples, we don't see that indeterminism in our everyday world. Well, that's, as I say, and really that would take me off in a different direction to continue talking about whether the future already exists or not. You see, but when we talk about time travel, I talked about the slowing down of time and getting to the future before everyone else. That doesn't require the future to be already there waiting to receive Alice. She's just getting to that future. It's unfolding more quickly for her. So she's getting to the future before everyone else. It doesn't mean the future has to pre-exist. So some would say, so this isn't real time travel into the future. Well, that idea about the nature of time and the slowing down of time that Einstein explained in his special theory of relativity in 1905 was further developed a decade later when he described his general theory of relativity. So in special relativity, he said, time is the fourth dimension. Time and space are mixed up. And that means that you can stretch and squash time in the same way that you can stretch and squash volumes in space. In general relativity, he said that space-time itself, the whole of four-dimensional space-time, can be warped, can be curved. What does it mean? Let's forget the idea of time for now. What does it mean to curve three-dimensional space? See, I can pick up a piece of paper and draw a picture on it and say, look, this is a two-dimensional surface, I've got a two-dimensional image on it, and I can fold or bend the paper. And because we have access to our third dimension, we can imagine how that bending takes place within 3 dimensions. But what does it mean to bend 3 dimensions of space? Well, we can get some idea mathematically. I'll show you, this is the one bit of maths in this talk. The sort of thing everyone learns at school, the sum of the angles, the interior angles of a triangle always is 180 degrees. And when I've given this talk to school kids, I always say, do you all know that? Yes, they all nod, they all know this. And I say, oh yeah, but your teachers have been lying to you all this time. They failed to point out to you that this is only true if you draw the triangle on a flat piece of paper. If you draw it on the sphere, of course, they don't add up to 180 degrees. The example is this. Apologies for being in the southern hemisphere, but talking about starting a journey from the North Pole. But imagine an explorer on the North Pole at point A who heads due south to some point B, hangs a left and moves east along to some point C, and then back north again to A. He has now traced a triangle. These are straight lines, as straight as you can draw them on a curved surface. That is always pointing south, that's always east, that's always north. He's got back to his starting point. There is a 90-degree right angle. There is a 90-degree right angle. Already those two give 180, plus the angle subtended at A, gives you a triangle with interior angles adding up to more than 180. And that's because it's drawn on a curved surface. Well, that's how you would, if you couldn't visualize, imagine an ant or a person on Earth, for instance, because the Earth is big. I forgot. You can fit a human there. If we didn't know the Earth was round, we thought the Earth was flat, and an explorer could trace this journey and arrive back to A again, and could deduce logically that the surface had to be curved, without actually moving, flying away from the Earth and looking back down on it to see that curvature. That's how we would understand the curvature of our three-dimensional space. The rules of geometry will be different because we can't visualize what it would mean to curve space. And curving four-dimensional space-time, as I say, adds another axis, the time. Mathematically, we can understand it, we can solve problems. Einstein's general theory of relativity is highly mathematical. In fact, Einstein himself had to learn a whole new area of mathematics in order to develop his theory. Well, Einstein, let me just stop that for a minute. Einstein's general theory of relativity says something else. It doesn't just talk about the curvature of space and time. It in fact gives us a whole new theory of the force of gravity. Now again, it was Isaac Newton, you might think, who was the person, he's the guy sitting under the apple tree and the apple falls on his head and he thinks, things fall. Okay, but people knew that things fell. Newton's genius was to realize that the reason the apple was falling to the ground was the same reason that the Earth went around the sun and the moon orbited around the Earth. That there's this invisible rubber band, invisible force of attraction that pulls any two bodies together. The apple isn't falling towards the Earth and the apple are moving towards each other. It's just that the apple, because it's so much less massive than the Earth, does most of the moving. So Newton developed his law of gravity, and it was fine. It was certainly fine enough to send the Apollo mission to the moon and back. Nevertheless, Einstein gave us a more accurate and deeper understanding of what gravity is. Einstein said you don't have to think of the force of gravity as this invisible rubber band force of attraction. Gravity, more fundamentally, can be thought of as this curvature of space-time. So when I said space-time is curved, you might think, well, why? Sounds good. Sounds like the sort of thing that sci-fi writers use. But the curvature of space-time is due to gravity. Gravity is what warps space-time. So you need something that, with enough mass to curve space-time around it. And something with a large enough mass, for instance, is a star. So when our sun runs out of its nuclear fuel and it's burning hydrogen, turning it to helium and other heavier elements, it'll just collapse under its own weight and be rather boring. It'll form what's called a white dwarf star. But when a very massive star, several times the mass of our sun, runs out of its fuel and collapses, the pressures explode outwards. You get shock waves blowing up the star in what's called a supernova. What's left behind could be these wonderful regions of space-time where gravity is so strong they've pulled in matter and light and nothing can escape. These are what we call black holes. So the center of a supernova, an exploding star, may be a black hole. We've known about black holes now for a few decades. In fact, Einstein's own theory of general relativity predicted that, because of gravity, predicted that black holes exist. Einstein thought that black holes was just a quirk of the maths. He didn't really believe that they were real. The first person to detect a black hole was a British astronomer by the name of Paul Murden. In fact, I work with his son, Ben, who's a professor in my physics department. And Paul Murden was the first person to detect a black hole. He was looking at a binary system of two stars. Most stars come as binary, as pairs. Our sun is quite rare in that it's a single star just with planets going around it. So you can imagine a pair of stars orbiting around each other. In some cases, if one of those stars turns to a black hole, all you see is a single star wobbling about. And the laws of physics tell you that something as big as a star can't be wobbled about by itself. There must be some invisible gravitational pull acting on it, and that is a black hole. But black holes are these regions of space-time that don't allow even light to escape. Gravity is so strong. And Einstein's theory of relativity describes what black holes are like and describes what it might be like inside. But of course, we don't know what is inside a black hole because no one's actually gone in to have a look around. And in any case, black holes are a bit like the afterlife. If you believe there's an afterlife, you don't know what it's like. No one can tell you because if they die and there is an afterlife, they can't come back and tell you. Well, it's like falling into a black hole. You might discover something wonderful, but you can never come out and tell anyone else about it. We do know that what black holes are like on the outside because they will suck in matter called an accretion disk, like water going down a plug hole. And as it goes down, it gets hotter and it gives off radiation, X-rays that we can detect. So that's a signature of a black hole. But once you get beyond the point of no return, the event horizon, what is it at the middle of the black hole? It could be a tunnel. It could be what's just called a singularity, the point with a final resting point of all the stuff of the matter that made up the black hole squashed down to a point of near zero size. But it might be that a black hole could lead to a tunnel to somewhere else, another black hole. The idea that the black hole provides a window possibly to either another part of our universe or maybe even to another universe. It's all hypothetical. It's theory because we don't know for sure. But the notion that it can give us a shortcut is something that very often in popular science books is explained in the following way. Imagine we are here in the Milky Way galaxy and we want to travel to another galaxy B far, far away. And you would think that provided you had a rocket fast enough, the shortest route between A and B would be a straight line. But that's only a straight line if space is flat. What if you could curve space? What if space could be bent over in this way? You could bend space, fold it over so that A and B are much closer, and you have this shortcut out of our space, this tunnel linking these two distant points. This became originally known as an Einstein-Rosen bridge. By the 1970s, the 1980s, physicists started referring to these things as wormholes. Of course, it's no good if a wormhole like this is basically a tunnel joining two black holes, because a black hole has an event horizon around it, so you go in one end, you can't come out the other end because there's another event horizon trapping you there. It's a bit like a prisoner who's trying to dig an escape tunnel from his cell, only to re-emerge in the adjacent cell. It doesn't really help him very much. In the 1980s, the American astrophysicist Carl Sagan was writing a book called Contact. It was then made into a Hollywood movie starring Jodie Foster. So Contact was about how we make contact with alien civilization, and they teach us how to build a device that opens up a wormhole, a tunnel, a shortcut through space. Well, the true story is that Carl Sagan, when he was writing the manuscript, he wanted to put together this idea, and after all, he's a professional astrophysicist himself, but he wanted to run it by some experts to make sure he wasn't just making stuff up, that he wanted his sci-fi novel to be based on proper, albeit speculative, physics. And he sent it to the preeminent best expert on Einstein's general theory of relativity at the time, a guy called Kip Thorne. And Kip Thorne had a read through the manuscript and suggested that, yes, you could mathematically think about a wormhole joining two different distant points that would provide a shortcut through space without any event horizons blocking or restricting two-way travel. And this became known as a traversable wormhole. So Kip Thorne he'd given his advice back to Carl Sagan. He said, okay, and you can write the novel and you can include these ideas. But very soon, Kip Thorne and his colleagues realized that they were oversimplifying the problem. The whole point of Einstein's theory of relativity is that it starts from the idea that space and time are mixed up together. So they realized that, Einstein didn't realize it, Kip Thorne did. Einstein wasn't alive by then, but I clearly am obsessed by that cartoon. Kip Thorne and his colleagues realized that if you bend space to generate this traversable wormhole, you also mess with time. And indeed, Einstein's general theory of relativity, the theory that talks about the bending of space and time, does say that time is actually slowed down by the force of gravity. So remember I said in his special theory, you can slow time down by traveling close to the speed of light. His general theory gives us a second way of slowing time down with the force of gravity. In fact, it's true that if my watch were running slow, I could hold my arm up in the air and speed it up. Because it's now slightly further away from the center of Earth's gravity, it's feeling a weaker gravitational pull, and time is allowed to run a bit faster. Obviously, I'd have to hold my arm up in the air for billions, maybe trillions of years. I haven't done the maths. And if it really was running slow and I was that bothered, I'd buy a new watch. But in principle, yes, time slows down. In fact, those of us who use sat-navs and smartphones that locate our position, the satellites that do that locating must take into consideration the idea that time can slow down. In fact, a satellite orbiting around the Earth, I'm not thinking of a geostationary one, but a satellite orbiting around the Earth, its clocks will be running slower compared to us because we see them moving relative to us. But a satellite is in orbit around the Earth. It's in free fall. It's not feeling any gravity. So its clocks are allowed to run faster because our clocks are being slowed down by gravity. So there's this balance between clocks on board a satellite that are running slower because of special relativity, but faster because of general relativity. It's not science fiction. The computers on board satellites, the computers that run, the control the satellites, have to take this into account in order to accurately measure time. Because how do you locate your position? You're pinging signals to 2 or more satellites, going and coming back again. You have to know exactly how much time it's taken to go and come back. Otherwise, you would not, without relativity theory, you would not be able to locate your position to any more accuracy than hundreds of meters, and that's something that will gradually get worse over time. So to locate your position to within just a few meters is thanks to Einstein's ideas about time actually being true. Einstein's general theory of relativity also tells us, however, that, because remember, slowing down of time just gets us to the future. I want to get to the point where asking the question whether we can travel back in time into the past. What if you were to get to the future and decide you don't like it and you want to come back to your own time? Thank you very much. Is that possible? Well, Einstein's general theory of relativity tells us that time travel into the past is also, in principle, possible. And Einstein's general theory of relativity is, so far, our best theory of the nature of time. So if it tells us that time travel into the past is possible, we should explore those implications seriously. Many physicists would argue, however, that time travel into the past can't be possible because that would lead to all sorts of paradoxes. Here are 2 brilliant physicists. One of them says, and this is true, Stephen Hawking has said, I think this is in his brief history of time, if time travel is possible, where are all the tourists from the future? His point being, if time travel into the past really were allowed, surely at some point in the future, we will have invented a time machine, and surely someone from the future will have come to visit our time today. This other brilliant physicist slaps him down. And in fact, there is a flaw in Stephen Hawking's argument, because if we were ever able to build a time machine that allowed us to travel back into the past, let's assume it is possible, you can only travel back to the moment that the time machine was switched on. Because of the way, in order to, however you generate this time travel device, you can only, the earliest moment you can hook up to is the moment it's switched on. Thereafter, you can hook it up to the future, and you can always travel back to that point, never before. So the fact that there are no time travelers amongst us today simply tells us that no one has invented a time machine, despite what you might find if you explore YouTube. And someone tweeted some wonderful site to me, some guy in America talking about how he had invented time travel and how the US government was stopping him from telling the world about it. And strangely, he didn't have much of a background in science. But why would physicists feel that time travel into the past is impossible? Well, because it leads to famous paradoxes. So I want to, might have time for both. Let me quickly run through a couple of paradoxes that the ways that I've enjoyed putting them together. I assume most people have seen at least one of the Terminator films. They're great fun. You're not supposed to take them too seriously, but anyway, for those few misguided souls who haven't seen this, so this is from the first Terminator film made back in the 80s. Arnold Schwarzenegger here is the android. He's the Terminator sent by the machines, the evil machines in the future, back to the present day, then 1980s, to kill the mother of John Connor. John Connor is the leader of the human rebels. So John Connor's fighting the good fight for humanity against the machines. And the idea is that if the Terminator can kill John Connor's mother before he was born, then he would never have been born in the first place. Of course, this being a Hollywood film, the Terminator doesn't kill John Connor's mother. because she's the goodie and he's the baddie. And this being a Hollywood film, John Connor sends his best friend back into the past to protect his mother. And he does more than protect her. He gets her pregnant, and she gives birth to John Connor. So John Connor's best mate is also his dad, and it's all delicious nonsense. But let's make a paradox out of it. Imagine the machines capture John Connor. Don't ask me why they don't kill him since they've caught him, but just for the purpose of this paradox, they send him back into the past to kill his own mother. So this is a variation on what's called the grandfather paradox. You go back to the past to kill your grandfather before he's met your grandmother, before she's given birth to your mother, before your mother's given birth to you. I've never understood why you have to skip a generation and why do you have to kill the male. Go back, kill your own mother. It's a cleaner experiment. It's much simpler. So John Connor is sent back to the past to kill his mother. They've given him some kill your mother serum so that he doesn't know what he's doing. They've given him his gun. What happens as he shoots her dead? Does he then fade away like in the Back to the Future films? Or does he just immediately, suddenly he no longer exists because he was never born? Well, imagine the police investigating this murder case, and there's a dead body and a bullet, and she's been killed. Who killed her? Well, it can't be John Connor, by the way. He's got the perfect alibi, never born in the first place. But this is the paradox. If he was never born, then she doesn't get killed. He kills her, so he's never born. So he never grows up to be a murdering time traveler, so she doesn't get killed, so he is born. So he does grow up and go back and kill her, so he isn't born, and so on. You go round and round for as long as you like until you get fed up with it. It's a paradox. There are physicists who would argue that time travel is possible, and there are one or two ways out of it. One way is to say that he can go back into the past, he can aim a gun at his mother, but he can't kill her. The fact that he's even there to try is evidence that he must fail. Clearly he must fail because she does end up giving birth to the guy holding the gun. Because you can't rewrite history. Okay, it's happened. But the traveling back into the past must link up. You must do whatever you do in the past to cause things to turn out the way they have turned out. But these physicists who would say time travel is possible, they don't explain why or how he fails. Does he come to his senses at the last minute? Does the trigger on the gun get stuck? Is he just a lousy shot? I think, is it in the film Linda Hamilton, is it? And she's quite fit, No, I'm in the athletic sense. So she does these backward flips, and you can imagine him firing and just missing until he runs out of bullets. What happens then if the machines bring him back to their time, dose him up with kill your mother serum, extensive shooting lessons, arm him up with lots of weapons, and send him back again and again to the past? Is he always going to fail to kill his mother because he must do? It's another one of those ideas which messes with the nature of free will. Suddenly, he's preordained, fixed not to kill her. Therefore, whatever he does, he's destined to fail. It's not a very satisfying conclusion or way out of the paradox. There is another way out, though. If you insist on wanting time travel into the past to be possible, then you have to, in my view, subscribe to an equally crazy theory. And that is that our universe is not the only reality. Now, physicists in the 21st century have a number of reasons why they'd like for there to be more than our universe. It explains away various problems in physics. It's one of the most popular ways of explaining away the weirdness of quantum mechanics, for instance, in something called it used to be called the many worlds theory, it's now called the multiverse theory. It explains why our universe is so perfectly designed for us. It may just be that our universe is one of possibly an infinite number of universes popping in and out of existence, and our universe just happens to be the one that was right for us. There's lots of other universes in which not only would life never have evolved, but maybe even stars wouldn't have formed. Atoms might be unstable because the electron's charge is too strong or too weak. And so the idea of parallel realities, parallel universes, is very neat. We have no evidence that it's true, though. It also resolves the problem of time travel into the past, because what happens now is to say that just as we have an infinite number of possible futures in front of us, whether or not it's preordained that we're going to follow a particular route or not is another matter, but all possible options of different futures lay ahead of us in the future. Likewise, it's possible that there are an infinite number of pasts that we could have come from. We only came from one along one history. But what if there were these parallel realities, like pages in a book, and we are stuck on one page, but there are all these other realities, other universes, other pages? It could be that the way we might hook up two different times and time travel into the past, that it would be almost inevitable that we would slide into a parallel reality. Because of all the possible paths that could be, only one of them is the path that we came along. But if you hook up to the past, via some wormhole or whatever, then it's overwhelmingly likely that you'll hook up with a parallel universe. In that universe, suddenly the paradoxes disappear. John Connor, in traveling back into the past, travels back into a parallel universe in which he can kill his mother. All that happens then is that he would never have been born in that universe, while the mother of the murdering John Connor stays living healthily in his original universe. So time travel into the past requires this extra bit of explaining. In order to get over the paradoxes, it says there have to be parallel universes. I want to end quickly then with the second short paradox. I call it the Mona Lisa paradox. Just to highlight again similar sorts of paradoxes. Imagine Leonardo da Vinci's just finished painting his great masterpiece. Leonardo da Vinci is also a great inventor, a great genius. Let's say he figures out how to build a time machine. So he's hammering away in his shed for several weeks and he puts this device together. He goes to bed that night rather nervous about how he's going to test his time machine. And when he wakes up in the morning and goes down to check it, sure enough, it's been activated. And there's something inside the pod, and it's a painting. And it's a note from Leonardo da Vinci himself in the future, who sent this painting back into the past to prove that the time machine works. It's a painting of a woman very much like his beloved Mona Lisa, same long dark hair, same bone structure, without her famous enigmatic smile. And he realizes it's her ugly sister, Mona Lot. And he's been avoiding having to paint Mona Lot for a while now. But here it is. He's got the set, and it's sent to him. And the note says, "I painted this painting on such and such a date, and I'm sending it back to myself, my younger self, to prove that time travel is possible." There are two paradoxes here. I mean, they can be linked, and depending on how you argue them, I like to split them into two. One is that at some point in the future, our Leonardo will become that future Leonardo da Vinci who sends the painting back to himself. What if he doesn't want to? What if he thinks, damn it, I've got the pair, I'm going to keep both paintings? What's the worst that can happen? Is some Time Lord going to come and tell him you threaten him with ripping the fabrics of space and time, that he has to send it back to himself? You see, he must send it back to himself because he does. That's how he got it in the first place. It's almost as though he's got no control over the fact that somehow the future must unfold such that he does send it back to himself. It's unavoidable. It's a paradox that he can't somehow keep it. Why not? Okay, well, let's say he does at the prescribed time that's detailed in the note, send it back to himself, go on into the future, quite relieved that rather unpleasant time is behind him. He's only got the Mona Lisa painting again. We've removed that problem. The paradox has gone. But there's still another paradox. You see, at a certain time in Leonardo da Vinci's life, he had in possession the Mona Lot painting. But at no point did he actually paint it. He found it in a time machine, kept it for a while, put it back in the time machine, sent it back to himself. There's this wonderful work of art, of creativity. That's why I use something like a painting by Leonardo da Vinci that is caught in a time loop forever. But at what point did Leonardo da Vinci put a brush to canvas and paint it? Again, this is a paradox. The only way out of it is to say, well, if there were parallel universes, then there'll be two Leonardos. Leonardo da Vinci, who paints the Mona Lisa painting, lives in a parallel universe, and he sends it to our Leonardo, who's able then to keep it for as long as he likes. It doesn't lead to any paradoxes. Do parallel universes exist or not? Well, of course, we simply don't know. The idea of wormholes, and I want to end on this, my last slide, is that wormholes, as was realized by Kip Thorne and his collaborators when he was checking the manuscript for Carl Sagan, wormholes allow us not only to hook two different points in space, they also give us the possibility of hooking two different points in time. It's inevitable. If wormholes could exist, then it's potentially possible that they could be used as a means of traveling back in time. But only if parallel universes exist. Well, unlike black holes, which we have overwhelming evidence for out in space, thankfully nothing too close to us, so we don't have to worry about being sucked up, despite tabloids in Britain when the Large Hadron Collider was turned on in 2008, being very worried that a black hole will be created and sucking us up. Black holes are real, but they're far away. Do wormholes really exist? We have no idea. They're another example of a prediction by a theory, albeit as far as we know, a wonderfully accurate and powerful theory, Einstein's general theory of relativity. But we have no evidence that wormholes really do exist in our universe. Likewise, the notion of parallel universes. There are very good, strong reasons to want to believe that parallel universes exist, but now we're straying into metaphysics and faith and belief. Physicists, all scientists, don't talk about, I believe this or that. You need empirical evidence. So that leaves the question of time travel into the past a matter of speculation. We don't know whether we can travel back in time. Our current best theory suggests it's possible, but it does lead to paradoxes. The hope is that one day we will either realize that there's a way out of it, that parallel universes exist, and that time travel into the past is possible. My bet, though, is that what is more likely is that we will find a loophole in Einstein's general theory of relativity that needs to be closed up, because time travel into the past probably isn't possible. That's a hunch, and that's not what physicists should be, the sort of language physicists should use. I've never been a fan of multiverse theory, of parallel universes. I can see the advantage, but as one physicist colleague of mine, some of you may know Paul Davies, who spent a number of years in Adelaide. He's now in Arizona. He's a theoretical physicist. He was quoted as saying that the idea of these parallel universes, the multiverse theory, he said, he was talking about it in the context of explaining away the weirdness of quantum mechanics. He said the multiverse idea is very cheap on assumptions. It's beautifully simple in that sense, but it's very expensive on universes. You know, suddenly, because you want time travel, or because you want to explain away the weirdness of quantum mechanics, or because you want to understand how come our universe is the Goldilocks universe, so specially designed for us, you propose the idea of an infinite number of parallel universes seems too far for many to go. So until we can fix that problem, the notion of time travel, I think, remains speculative, and it remains in the realm of science fiction. Thank you very much.
Jim, thank you very much. I'm Karen Day, the Dean of Science. I'll confess I'm a sci-fi geek, so very delighted to hear the limits of time travel. I think we'll open up for some questions for a few minutes. Yes, please. In the check shirt there. There are microphones coming, and I just need to tell you this question session will be recorded.
Hi, a comment and a question. I'm always amused in science fiction stories that in a universe where there's no fixed frame of reference, there'll always geolocated. In other words, they end up in the same place on Earth, just in a different time. My question, in reference to navigation of satellites, 20,000 kilometres, I thought I heard you say that it's due to free fall. I thought there's, you've got time dilation due to velocity and another one due to a changed gravitational field strength. Comment on free fall, please.
Well, if it's a satellite that is in orbit around the Earth, that's not in geostationary orbit, if it's orbiting the Earth, then it's constantly falling towards the Earth. So it's not feeling a gravitational field. If it's geostationary above a certain point above the Earth, then it's feeling it's in free fall. If a satellite is in free fall, that means it's not feeling any gravitational field. It's weightless.
Gentleman here. Can you wait for the microphone, please? Thank you.
With the satellites actually falling, just take the International Space Station, for instance, it's actually bouncing on the atmosphere. And they actually have to constantly, I think they use rockets or something to actually blast it up. It's because it's the radio signals are a little bit closer or something, I don't know why. But it's actually always falling and then just like occasionally lifting up on the atmosphere.
Well, there might be some uplift from whatever's left of the atmosphere at that height, but it's certainly, you could imagine anything orbiting anything, something, or the moon, or some satellite orbiting Mars where there's no atmosphere. If it's orbiting, it's in free fall, and so it's constantly falling towards the ground. But because it has a component of velocity that's tangential, then it's falling at an angle. It's always falling, but dipping round and round, and falling around at a constant radius from the surface of the Earth. So it feels no gravity, so time would be allowed to run faster than if you're feeling a force of gravity.
The gentleman in the blue, there.
My question's more around the time travel into the past. That we're in a galactic arm, we're swinging around a solar system, so we're not standing still. If you travelled into the past, either we haven't arrived there yet, or you're not going to arrive on a point on the planet. Is that factored into these concepts?
Yeah, I mean, in sci-fi movies, it's always, you flick a dial, 1969, and you come out and you're in the same room, or at worst you come out at the same point before that building was built or whatever. If time travel were possible, let's say via a wormhole. Now, one idea is that you could build a wormhole where the two mouths are sort of close to each other, and then you go into one, you can come out the other because you jump out of space. Imagine taking one of those mouths of the wormhole in a rocket, traveling very fast, close to the speed of light, accelerating and decelerating so that it slows time down, and then bring it back again and stick both ends of the wormhole back in your wormhole lab. Now you go in one, you'll still come out the other one, you know exactly where you'll come out, but you'll come out in the past or the future of the first one. So you can imagine a wormhole that is, the two ends are out now by a day. So you can jump into the wormhole and come out yesterday and go for a meal and whatever, and then come back and join yourself. You can both jump in, you can both come out. Okay. It leads to paradoxes, but the idea of a wormhole time machine means, yes, you can precisely define where you want to come out the other end in the past.
The gentleman here with the purple shirt there.
You mentioned that the physics in the movie Contact was slightly oversimplified. I just wonder what the movie would have looked like if they'd got it right.
I don't think it was oversimplified in as much as it didn't... the point was that... I don't know about I haven't compared the movie script carefully with Carl Sagan's book, but the point of the novel is that it relied on general relativity and the predictions of general relativity that were perfectly fine. Not necessarily what we would have in our own universe. I mean, it wasn't breaking any laws of physics or any laws of general relativity. It was pushing the predictions of general relativity as far as possible, the idea that you could hook up to different points in space-time. So mathematically, essentially, if you curve space-time to create a black hole, you have this event horizon around it. You can curve space-time in a different way mathematically without having any event horizons. That was Kip Thorne's idea. Whether we'll ever be able to physically create such a curvature in space-time is another matter. In fact, it's been suggested that in order to hold such a wormhole open, the scaffolding that stops it from collapsing again and disappearing requires it to be made out of a certain kind of material, which imaginatively physicists have called exotic matter, which has the strange property that it has negative mass. You know, what the hell does that mean? Negative, something that, you can imagine something weighing 5 kilograms or 1 kilogram or being weightless, but what does it mean for something to weigh minus 5 kilograms? We can think about, in quantum mechanics, the idea of negative energy. You can suck energy out of the vacuum when energy doesn't exist, subject to certain quantum rules. And since energy and mass are interchangeable, you can argue the point that E equals mc squared. So if you can have negative energy, you can also have negative mass. But to have enough negative mass to make a wormhole, say it's not breaking any laws of physics. It's just not very realistic.
There's one question right at the back there, centre back. Perhaps while we're waiting, I'd like to use chair's privilege. My mind as a biologist was wandering off into biological time where as we get older, our telomeres shrink and that's the correlate of ageing. So I'm thinking in the time travel concept, what would we be doing with our telomeres? We'd have to have parallel universes, I think.
Well, I have to say, I mean, on that issue of time speeding up as we get older, I'd always had this, the naive, which I gather is wrong, idea that, a year goes by very quickly, from one birthday or one Christmas to the next, much more quickly as you get older compared with, say, a child. And that's because it's a smaller and smaller fraction of your life. But I gather it's actually because we don't make so many new memories as we get older. We build into sort of routines of life, whereas when you're young, everything you do is new, everything you do is for the first time. So creating so many new memories allows time to slow down. So that's the way to stop time speeding up as you get older, is to do lots of new things.
Right. I'm more thinking about our DNA sequences and
Okay.
and them getting shorter as we get older, certain sequences at our telomeres. Anyway, the question at the back there.
Thank you. If black holes are the opening to wormholes, shouldn't we, where all light is sucked in, shouldn't we have been able to detect the other end where all light is spewed out? There was at some point the suggestion that the other end of a black hole would be a white hole. So even has a name, you see, that everything goes into a black hole, comes out the other end and spewed out. But then they did the calculations and realized that white holes would be unstable and the matter would fall back in again and revert them into black holes as well. Yeah, we've not seen any such hole in the universe that's spewing out stuff. The black holes we see are always sucking matter in. And it may be that the interior of a black hole leads nowhere. It may just be that that's it. You get to the end, the edge of space-time, the singularity, there's nothing beyond it. And as a black hole sucks in more and more stuff, it just gets bigger and bigger. It just feeds and grows. But there is an example of the opposite of a black hole that's throwing everything out, and that's our Big Bang singularity, the birth of our own universe. You can think of our universe as being a white hole. It's throwing it also marks the edge of space-time. It's the beginning of space-time. Same as a black hole is the end of space-time. Our Big Bang is the beginning of space-time, and everything that came out of it was spewing out of that initial singularity. So there are ideas along those lines, but certainly no one's ever seen two holes in space. One is a black hole and the other is a white hole.
I guess any one of those I'll let you choose.
In the example you gave on the twins paradox, Alice and Bob, so you're saying Alice was on the rocket and going really fast. Isn't that true that relative to Alice, Bob is also going very fast the other way? So how did that work? I never figured that one out.
Yeah, well, that's why this is called the twins paradox. It's a paradox of special relativity, and it's a very nice example when special relativity is taught. Because you're right, if Alice were just to travel away from Earth in a straight line, she could, since all motion is relative, she could equally say, I'm not moving, and it's the Earth that's moving in the opposite direction, and come back again. The way to explain this is that the two situations are not symmetrical. Alice has to speed up, or even if she's got up to speed as she goes past the Earth, when she gets to a final point, she has to slow down, turn around, and then speed up and come back again. And in fact, in reality, it's that speeding up and slowing down, the acceleration and deceleration, that is permanently making her less time for her to have elapsed. So when I talk about it, I talk about her zipping around the universe. And that's my way of sort of, without actually explicitly describing it, I'm saying she's not traveling in a straight line. She's going around zipping, in all different directions. So she's constantly accelerating and decelerating, and that's what's slowing her time down. And one of the things Einstein that led him to general theory of relativity is something called the principle of equivalence, which says that gravity and acceleration are equivalent. If you're in a lift and the lift shaft breaks and it falls, or you're just in a lift that's going up, in principle you can't tell whether you're accelerating or whether you're just feeling Earth's gravity. So acceleration slows time down in the same way that gravity slows time down. And Alice is accelerating, and that's what's doing the damage. That's what breaks the symmetrical picture between her and Bob.
Take one last question. Oh, friend here.
Thanks. Hi, of the sci-fi films that you've seen or know about, which one do you think best deals with time travel?
I thought you just said, what's your favourite sci-fi movie? That would be so much easier. There was a... Well, not loopers, anyway. Is that loopers? I'll tell you which ones that don't do.
I guess what you just described, it sounds like Planet of the Apes, maybe?
Yeah, okay, well, that's right. But I think that the movies that do time travel well are the ones that don't get into too much detail. Because then they skim over the problem. As soon as they start trying to be clever, you can if you want to find paradoxes, you will find them, and that sort of ruins it for anyone who knows anything about relativity theory. So yeah, I think what was the one? No, it's not going to come to me. I could stand here scratching my head. But favorite sci-fi movie is The Matrix, I think. But you didn't ask me that. I just thought, just in case anyone was wondering.
Okay, I think we'll wrap up now and thank our speaker for an excellent talk. And it's such an important, I think, area to have someone as excellent as this in public understanding of science. We're sitting in Australia at the moment where we no longer have a Minister of Science. And so I think the onus on us as scientists is to get out there and really engage with the public. And you are really a stellar example of what we all should be doing. So thank you very much.